This meeting is being recorded.
In Chapter 15, our textbook introduces us to what's referred to here as nuclear magnetic resonance spectroscopy. So similarly to infrared spectroscopy, we're going to be utilizing a source of electromagnetic radiation and seeing how matter, or our compound of interest, interacts with that electromagnetic radiation. So for nuclear magnetic resonance NMR spectroscopy, we utilize radio waves, whereas with infrared spectroscopy, we utilized infrared radiation. So what exactly is this type of spectroscopy? Well, we're going to be looking at the nuclei of an atom. So that's where the term nuclear comes from. We're going to apply a magnetic field. So hence the term magnetic, and then we're going to see a flipping or a change in state of our nuclei, and that's where this term resonance comes from. So a change in state, just like when we saw resonance structures or movements of electrons from one orbital to another. Now we're going to see a different type of resonance where the nucleus is changing its state. So from that, we can actually see more detail as far as the carbon or the hydrogen nuclei that are present in an organic compound. This will be our focus for this semester with NMR spectroscopy, but there are other types of nuclei that can be responsive, and we'll talk about what the requirements are. But in general, again, this is just that interaction between the electromagnetic radiation, light, radio waves, in our case here with NMR, and the nucleus, so the matter that we're looking at. So we can find, instead of just functional groups, now we can actually pry more into the structure or connectivity of these carbon atoms and these protons. So what exactly happens here is that protons and neutrons in a nucleus behave as if they are spinning. And if an atom has an odd number, so this is important here to note that we cannot use an even number of protons or neutrons in combination, we generate this net nuclear spin. So examples of atoms that have these odd number of protons or neutron combinations, we see hydrogen here, also called protium, when it only has that atomic mass of 1. We also have carbon-13. So this specific isotope of carbon is what we can analyze using this method, but carbon-12 would have an even number of protons and neutrons. So carbon-13 is present in much lower quantities. So we'll talk about how that affects our analysis. And then there are some other atoms such as nitrogen-15, fluorine-19, or phosphorus-31. So these three here we're not going to look at in detail, but note that carbon and hydrogen are not the only atoms that can have NMR spectroscopy utilized. So what happens is this nucleus spins, and this creates this magnetic moment. And that term magnetic moment we can equate with a magnetic field. So what does this mean for our analysis? Well, we create this magnetic moment from the nuclear spin. So therefore, this magnetic field is created. So we can compare to just a magnet with a north and south pole. These types of forces that are invisible to us, but we know exist. And what spectroscopy, NMR spectroscopy, does is it applies an external, here we go, magnetic field here, this B sub 0 that's indicated. And when we apply this external magnetic field, the nuclei of our atoms will align with or against that magnetic field. So we can see in image A here that there is no applied external magnetic field, but then in image B, we can see these nuclei either designated as alpha or beta here, and their arrows pointing either against or towards this external magnetic field. So what happens then when we apply this in magnetic field, our, our atoms align, and they can align either with the applied magnetic field or opposing it. So if we have a spin state that we say is opposing the external magnetic field, that will be a higher energy spin state, right? It takes more energy to exist in that state. And we can see an example here. So our applied magnetic field is shown in that blue arrow, and the spin state of our specific nucleus is in the beta spin state, and you can see here they are opposing each other. They're going in opposite directions. But then if we have on the other side here, we see this alpha spin state. This would be a lower energy spin state because this nucleus is aligned with the external applied magnetic field. So we can see over here in this energy diagram, both of these spin states relative to one another. So we can see our alpha spin state, and again, our applied external field is in this direction. So the alpha spin state pointing in the same direction, lower energy spin. And then we have our beta. Again, that's at that higher energy up here. So when an atom in the alpha spin state is exposed to radio waves, so here's where radio waves come in to NMR spectroscopy, it causes a flip, a spin flip, when just the right amount of energy, that delta E that we're shown here, is that difference in energy between the alpha and beta spin state. When this exact amount of energy is applied, these photons are absorbed, right? That light energy, so that wave of photons is absorbed, and then we have this spin flip result. So we go from alpha to beta spin state, and then that's how we can measure the energy gap, right? So we actually measure this through NMR spectroscopy, and depending on the environment of the proton, we'll start with proton NMR. So depending on the environment of each of these hydrogen atoms, our nucleus would require more or less energy to flip, to have this spin flip occur. So we're going to utilize that knowledge and create this resonance type of environment. So we can see again, our alpha spin is flipped to a beta spin when that energy, that exact amount of energy is absorbed, and then they create this type of resonance when they change from one state to another. So again, this is very different from resonance you've heard about before, as far as electrons moving to different orbitals. But now we have this change from alpha to beta spin state, and that spin flip occurs, and we can then probe different molecules to see the different protons that are in the structure. So we'll look at this in more detail in the next section.